Okay, everyone, we're going to finish up chapter 14 with this third video lecture. This is going to be a short one because I only have a few slides left. So the last thing to talk about in this chapter is the use of confidence intervals as a tool for testing hypotheses. Up to this point in this chapter, we focused mainly on a significance test using a p-value. But now I'm going to show you how to use a confidence interval instead of a p-value to basically arrive at the same conclusion, okay? So we've already talked about the fact that a two-sided test is symmetric because in a two-sided test, you're dealing with both tails of the sampling distribution curve, all right? So let's say we set our confidence level at 95%. That means that our alpha is going to be 5%, right? So alpha is your significance level for your p-value. It's your p-value cutoff. Anything below 5% or 0.05 would be significant. Anything above it would be non-significant, as we've talked about. But if we set our confidence level at 95%, then that means that we are defining 95% of the area of our curve. We're defining 2 points on the x-axis within which 95% of the curve falls. That means that 5% would fall outside the curve, 2.5% on this tail, 2.5% on this tail, okay? So in a two-sided test, our confidence level equals 1 minus alpha. So if we set this at 95%, 100% minus alpha, which would be 5%, gives us 95%, right? Your alpha and your confidence level are always the inverse of each other. Okay, so let's talk about the logic then of a confidence interval test. So previously, I don't remember what chapter it was, we talked about an example of measuring bacterial density in a solution, okay? Again, let me fill in some things here. All right, so we found a 99% confidence interval in that example for the true bacterial density with a sample mean of plus or minus or margin of error equals 28 plus or minus 1.5 million. So 28 million bacteria on average in our sample, plus or minus 1.5 million. That's a 99% confidence interval. Or another way to state that is that we have a confidence interval of 26.5 to 29.5 million bacteria per mil. We are 99% confident that the true population mean density lies within those two numbers, within that 99% confidence interval. So the question is, with 99% confidence, could the population mean be 25 million per mil? Could it be 29 million per mil? Well, we have our confidence interval shown by the black double-headed arrow here, right? This would be 26.5 to 29.5. So if we look at the sample mean of 29 million first and ask, could that be representative of our true population mean, we see that 29 million falls right here. It's within our confidence interval. So that means that that sample mean of 29 million is not different enough from our actual population mean to assume that the difference is anything other than random sampling variation. So in that case, we can't reject our null hypothesis that our population mean is 29 million from that sample mean. All right. Could our population mean, however, be 25 million? Well, 25 million falls way over here. It's outside the boundaries of our confidence interval. So that would mean that there's so much difference between that mean and our true population mean that the difference is not at all likely to be due just to random variation. It must be a real biological effect. In that case, you would reject the null hypothesis and accept the alternative. So a confidence interval here gives, as it says, a sort of black and white answer, right? You either reject the null or you don't. But the really useful aspect of a confidence interval is that it also estimates a range of likely values for the true population mean. So it gives you an added bit of information that a simple p-value test doesn't do, okay? A p-value quantifies how strong the evidence is against the null hypothesis by giving you the likelihood of getting, or the probability of getting a sample mean that whatever it is. But if you reject the null from a p-value, it doesn't provide any information about the true population mean. And as I said in class today, typically software packages will give you some combination of these two. Okay, if you tell Minitab to do a significance test, it'll give you the p-value, but it will also calculate and show you the confidence interval as well. Okay. All right. So confidence intervals versus tests of significance, right? So confidence intervals, again, we're going to quantify the uncertainty in an estimate because they give us a range along the x-axis within which the true population mean might lie. So by giving you a range, an area under the curve, they are telling you something about the variation around that population mean, that estimate of the population mean. Tests of significance with p-values evaluate statistically whether a hypothesis makes sense, is reasonable or not. Okay, so let's look at this example here. So the national average birth weight is 120 ounces. Okay, so we have a normal population distribution with a population mean of 120 and a standard deviation of 24 ounces. All right. We take a simple random sample of 100 low-income mothers, and we find that gave an average sample birth weight of 115 ounces. So the question here is, this 115 is lower than 120, obviously, but is that difference just due to random sampling variation, sampling error, or is it evidence of low-income mothers actually giving birth to lower weight babies, presumably because of lower socioeconomic status, less access to good nutrition, that kind of thing, right? So, question is this statistically lower than the national average at significance level 0.05? So confidence level of 95%. We have two hypotheses. Our null hypothesis is that the population mean among the poor is 120 ounces. That's a way of saying that the population mean of the poor and the population mean of everybody else is the same, so we only have one population with regard to birth weight. The alternative is that the population mean among the poor is lower or less than 120 ounces. All right, so this is a one-sided test, one-sided alternative. Calculate a z-score, so I gotta fill in again. So z again equals, okay, our sample mean minus our hypothesized null mean divided by the population standard deviation over the square root of n, okay? And we do all that math, you see right here, and we get a z-score of 2.08. Actually, negative 2.08. Well, according to the empirical rule, right there you already know that you're outside your 95% confidence interval, because two standard deviations, and this is 2.08 standard deviations, 2 standard deviations away from the population mean would give you 95%. So we're outside that by a little bit, so we're better than 95% certain or confident, okay? At 2 standard deviations, our p-value would be 0.05. We're a little bit outside that toward the tails, so our p-value is going to be smaller. If you look up a z-score of minus 2.08 on table B, it gives a left area of 0.0188, or a p-value of 1.88%. Table C, we find the p-value is between 1% and 2%, which matches this, but table C is going to tell us what confidence what confidence level that translates into. So I'll show you in a moment. So with these results, we can conclude that random variation from random sampling alone would give us such a low average birth weight in only about 2% of cases. Our cutoff is 5%. So we're more confident than we need to be to reject this null hypothesis. So we have significant or statistically significant evidence, a p-value less than 0.05, that babies born to poor mothers do, on average, weigh less than 120 ounces. All right, so let's look at table B first. So we had a z-score of minus 2.08, so minus 2.0, and then 08 here. Drop it down. That's our area to the left. That's our p-value, 0.0188. All right. Now, whoops, sorry. So I guess that was it. So I thought I had table C to show you. But anyway, that's an example of a significance test, okay? It basically takes a subjective process comparing 115 ounces to 120 ounces and saying, just sort of shooting from the hip that, yeah, I think that's probably due to, lower socioeconomic status, whatever, in poor mothers. It takes that subjective determination and converts it to an objective one by setting objective thresholds, the p-value, right, the significance level, 0.05. Our p-value turned out to be smaller than that, so we can safely say, or reject rather, the null hypothesis, which says there'd be no difference in birth weights between poor mothers and everybody else, and accept the alternative, which says that poor mothers do give birth to lower weight babies than more affluent mothers. We would accept that alternative hypothesis. And we did it in a very objective, black and white sort of way. And again, if you do your statistics correctly and you come to that conclusion based on a p-value, no one can argue with you. This is the way it's done. This is the way that we come to conclusions in the sciences. That's why science is objective. All right. Okay, so that wraps up chapter 14.